Welcome to the 37th lecture on computational mathematics with SageMath. In this lecture, we will explore inner product in SageMath. So, first let us start with standard inner product on Rn. This we have seen earlier. So, for example, if you have two vectors u and v in R4, then you can define or find an inner product of the dot product of these two vectors using star command. So, if you say u star v, it will give you the dot product of u and v, or you can say u dot underscore product in the bracket v. So, u dot underscore product is a method inside SageMath in order to find the dot product. You could also mention u dot inner underscore product. So, by default in Rn, inner underscore product will give you the standard dot product. Of course, you can also find norm of a vector, that is length of a vector, using norm command. Of course, you can also find norm which is in various forms like L1 norm or sup norm. So, I will leave this as an exercise. Try to verify these two properties of norm, that is triangle inequality, and this is what is known as parallelogram law, that is sum of the diagonals square. This is sum of the diagonals, length of the diagonal square is going to be twice the length of squares of each side. Right. Now, let us look at how we can define inner product on a vector space. So, we will work with vector space over R. If it is vector space over complex field, then definition will be slightly different. Okay. So, suppose you have a vector space V over R, then an inner product on V is a map from V cross V to R, satisfying the following properties. The first property is, if you take inner product x with x, that is always non-negative, and inner product x with x will be 0 if and only if x itself is 0, and it is commutative. So, inner product x with y will be same as inner product y with x. This is where the inner product defined on a vector space over complex field will differ. That will not satisfy this commutativity, rather it will be slightly different. Next property is associativity. So, or you can say it is linear in each of this the component. So, if you take x plus z, take inner product with y, this is same as inner product of x with y plus inner product of z with y, and this is true for every x, y, z in V. And similarly, if you have x inner product with y plus z, this is x inner product with y plus x inner product with z. And then next one is, if you take alpha times x inner product with y, this is same as alpha times inner product x with y for any real number alpha and for any two vectors x and y. So, any map from V cross V to R which satisfies all these four properties is known as inner product on V, and then the vector space V along with this inner product is known as inner product space. So, for example, if you look at Rn with dot product, that you can check that the dot product in Rn satisfies all these properties, and hence it is an inner product. Let us look at few other examples. So, but before that, let me also define, once you have inner product defined on a vector space, then you can define length of any vector, that is we denote by norm of x. We read this as norm x, and this is defined as positive square root of inner product x with itself. It is not x with y, it is x with itself, right, and this is what is called norm of x with respect to this particular inner product, right. So, here you should notice that this since norm of x with itself is non-negative, you can find its square root, and since length we want length, it should be non-negative, therefore, we take non-negative square root. And of course, if I take norm of x square, that is nothing but inner product x with itself. So, in this case this norm is induced by this inner product. So, once you have inner product, then you can define norm. Of course, one can define norm function independently, and one can relate this, right. Similarly, if you have two vectors x and y, we say that they are orthogonal to each other if inner product x with y is 0. So, in that case we say two vectors are orthogonal to each other. In terms of dot product, you had x dot product with y is equal to 0, but that can be extended to any inner product space. And then this norm and inner product is related by this very actually important inequalities, which is known as Cauchy-Schwarz inequality. And what does it say? If you take V, an inner product space, and take any two vectors x and y, look at the mod of inner product x with y, this is always less than equal to norm of x into norm of y, and this equality will be true if x and y are linearly independent. So, that is the inequality, which is very powerful and very useful inequality, at the same time very important. Now, actually this Cauchy-Schwarz inequality gives you a way to find angle between two vectors x and y. So, let us look at this inequality. For example, if this inequality, let us assume that both x and y are non-zero, because if any one of them is 0, then it does not make sense to talk about angle between 0 vector and some other vector. So, let us assume that both x and y are non-zero. In that case, if you divide this inequality on both sides by norm x norm y, this would mean that modulus of inner product x with y upon norm of x into norm of y will be less than equal to 1. That is same as saying, if I remove this norm, this mod, then it would mean that minus 1 will be less than equal to inner product x with y upon norm of x into norm of y less than equal to 1. So, this particular quantity will lie between minus 1 and 1 for each x and y, non-zero x and y, and you know a function which always lie between minus 1 and 1, and that is cos theta. So, if theta is angle between two vectors x and y, then cos of theta is nothing but inner product x with y divided by norm of x into norm of y. In particular, theta will be cos inverse of this quantity. So, this definition actually is motivated by this Cauchy-Schwarz inequality, right. So, let us look at some examples. So, we have one example of inner product on Rn, which is dot product, right. Okay. Now, let us fix a positive definite real n cross n symmetric matrix A, and then on Rn we can define x inner product with y as y transpose Ax. Actually, this y transpose Ax can be thought of as dot product with y with Ax. You see, X will be a vector in Rn, y is also vector in Rn. So, y dot product with Ax makes sense, and that is nothing but this y transpose Ax as a matrix multiplication. So, one can show that this is an inner product on Rn, and in fact, all the inner product in Rn, any inner product in Rn would appear in this form. Okay. So, let us look at an example. So, suppose you take this matrix A, you can check that this matrix A is positive definite. So, there is inbuilt function to check positive definiteness of a matrix. Of course, this is symmetric, and define this inner product u v as u v transpose A u. So, let us look at this. So, A is this matrix, and we can check whether A is positive definite. The answer is true. You can also check whether A is symmetric. So, A dot is symmetric will give you true if it is symmetric matrix, right. So, once you have this, then let us define inner product. I am giving this name as INPA. A stands for this matrix of u and v is, what should it return? It is just dot product of v with the matrix A u or the vector A u. So, that is the inner product. Now, you can take any two vectors. For example, let us take standard unit vectors u1 and e2, and let us find what is inner product of u1 with respect with u2. So, it is -1 in with respect to standard dot product. E1 and E2 are orthogonal. So, it would be 0, whereas in this case they are not orthogonal, right. Similarly, you can find what is the length of this vector E1 with respect to this inner product. So, that is the square root 2, and it is not 1. Okay. So, you can have some vectors which are unit with respect to a standard basis in Rn, whereas with respect to some other inner product it may not be, or it may no longer be unit vectors, right. Okay. Let us take another example. Let us look at this vector space C01, set of all continuous functions on closed and bounded interval 0 to 1. We have seen that this is a vector space over R. So, we can define inner product of any two functions f and g in C01 as integral from 0 to 1 of f(x) times g(x). So, it is easy to check that this is an inner product. This will require little bit of calculus or real analysis, especially when you want to show that if inner product of f with itself is 0, then f itself is 0. That will use continuity of the function, right. So, let us define this inner product. So, I am giving the name INP underscore C01 of f and g, and what should it return? It should return integral of f(x) gx and x going from 0 to 1, right. So, that is the inner product, and we can now suppose we take two functions, continuous functions, f(x) equal to x plus 1, gx equal to x square, and then we can find inner product of f with g. So, it will find integral of x plus 1 times x square, integral from 0 to 1. So, x plus 1 into x square is going to be x cube plus x square, and its integral will be x to the power 4 by 4 plus x to the power 3 by 3, and when you add this, when you evaluate this, you will get 7 by 12, right. Similarly, you can find length of any vector. In this case, length of, let us say, x plus 1, this is square root of inner product underscore C01 f with itself, this is square root 7 by 3. Similarly, you can find length of g, right. In case you have this constant function 1, then its length is going to be 1. So, this is again 1, right. You can find out various concepts regarding this. So, maybe try to verify Cauchy Schwarz inequality for this inner product. So, if I look at say inner product, so INP underscore C01 of f with g and take the modulus of this. So, this is INP, take the modulus of this, that is absolute value of this, So, this is 7 by 12, and is it less than equal to norm of f into norm of g, that is what we want to check. So, this is f comma f okay. So, this it is, let me say whether it, let us give bool, yeah, the answer is true. So, if I have to check this inequality, you can ask, you can say bool absolute value of this is less than equal to this. So, the answer is true. So, it satisfies Cauchy-Schwarz inequality, right. That is a verification of Cauchy-Schwarz inequality. Next, let us look at this MNR, set of all n cross n matrices over R, and on this we can define inner product as inner product of A and B, two matrices A and B, as trace of A with A into B transpose, A into B transpose, right. So, let us define this. So, this is definition, here we am calling as INP MNR of A and B, it should return A into B transpose and then take trace of this. So, for example, if I take two matrices, A is equal to this matrix 3 by 3, B is equal to this 3 by 3 matrix. So, we can find inner product of A and B, this is 77. You can also find length of this matrix with respect to this norm, right. So, you can also define inner product on P and R, this is set of all polynomials of degree less than equal to R. One way to define is this, take any two polynomials P and Q of degree n in over R, and define inner product of P with Q as P0 into Q0 plus P at 1 into Q at 1 plus dot 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 P at n into Q at n, and it is very easy to check that this is an inner product. So, how do I define that? So, we will say INP POL, that is the name I am giving, and F and G, and this is n is stands for the degree here. So, and take f of x at I, g of x at I, and multiply these two, f x at I and g x at I, and run I over range n plus 1, because it has to go from 0 to n. So, n should be included. So, 0 to n plus 1, and then take the sum, that is the inner product. Of course, you could check instead of 0 1 0 to n whether we can take any n plus 1 real numbers. For example, P at let us say any n plus 1 real number a1 a2 a n plus 1. So, P at a1 times q at a1 plus P at a2 times q at a2 plus dot 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 P at a n plus 1 q at a n plus 1, whether that is also an inner product, that you can check, right. So, let us see if I have two polynomials of degree 3, and then we can find its inner product of f with g using INP POL and so on, right. Similarly, you can find length of each of these polynomial, right. Once we have an inner product on a vector space, we also saw how to define orthogonal vectors. When do you say two vectors are orthogonal with respect to that inner product? Now, let us extend this idea of orthogonal projection, which we have done in case of dot product in Rn. So, if you have a inner product space and you have a vector v and a vector u, say you want to find orthogonal projection of v onto u, see the definition which we have looked at for dot product, that dot product will be replaced by inner product, that is all. So, this is you take perpendicular from V to this U, this line U, this is the origin, and then this particular vector, this green, is called orthogonal projection of V onto U. So, and how do we obtain this vector? So, actually this will be a scalar multiple of U. So, this projection of V onto U will be some t times U, and since this is perpendicular to this vector dot product with U will be 0, and what is this vector? This vector is actually, if you look at this t times U, this vector plus this vector plus this vector which is V minus t times U, that is this vector. So, this V minus t times U will be orthogonal to U, and that will give you what should be value of t, and it turns out that scalar is inner product of V with U divided by norm of U square times norm of U square. Therefore, the projection of V onto U is given by inner product of V with U divided by norm of U square times U. So, that is the. So, let us define a function for orthogonal projection. I am defining this as projection PROJ V with U, that is V onto U, and with respect to the inner product, right. So, that is the inner product here. So, then what it should return? The inner product of V with U divided by norm of U square times U, and then return that. Okay. So, let us look at, for example, if I have two polynomials, this is the inner product with respect to which we want to find orthogonal projection. So, this we have already defined. So, I do not need to do it again. Let me just a second. Since there we had given here n in the definition, let me remove that n, because here inner product I am taking as inner product V with U. So, of course, one can take care of that definition as well. So, it is take this inner product, define this INPOL of two polynomials f and g as this. So, this is a polynomial of degree 3, and f and g are two polynomials. Let us see what is orthogonal projection of f onto g. So, that is the orthogonal projection. Now, you could also verify that if I take for example, I will call this as let us say H, which is orthogonal projection of f onto g. This is H. Let me do it in a different cell. This is my H, and suppose we take g of x, or let me say g minus f. G, we are taking orthogonal projection of f onto g. So, it will be g minus f, this inner product with INPPOL with g, this should be 0, right. So, this is, let us see, we have obtained the projection of f onto g with respect to this inner product, and we are taking what is it? We are taking f, it should be f minus h, the inner product with f minus h inner product with g, this should be 0, correct. So, this is the verification that what you have obtained H is an orthogonal projection of f onto g, right. Similarly, let us take with the same polynomials f and g, we can define what is orthogonal projection of f onto g with respect to inner product that we have defined on C01. So, these polynomial f and g can also be thought of as an element of C01. So, if I take orthogonal projection of f G onto F with respect to this inner product, that is inner product from inner product which is integral from 0 to 1 Fx Gx, that is this one, right. Similarly, let us take another example. So, suppose we want to find a vector v in P3R, that is a polynomial of degree less than equal to 3, which is orthogonal to this vector, right. So, how do we obtain? So, if I want orthogonal to this vector, we can start with any vector in this vector space. So, let us say we start with x to the power 3 x cube and take orthogonal projection of x cube onto x square plus x plus 2, and then take out that orthogonal projection component, that will be a vector which is perpendicular to Fx, which is equal to x square plus x plus 2. So, let us see that. So, we define f of x is equal to x square plus x plus 2, Gx as x cube, and define Fx is equal to Gx minus this is not 3, this Gx minus orthogonal projection of F onto G. So, here it should be inner product of G onto F, right. And now, let us check whether P is P which is perpendicular to F. No, this 3 is right, that is correct. So, we have found a polynomial this which is orthogonal to this given polynomial x square plus x plus 2, right. If I change this, for example, if I say x cube plus x square plus x plus, let us say 1, and G, take any G which is different from this F, this will work. So, now again you can check whether P is perpendicular to, that is correct, right. Similarly, you can find orthogonal projection of a matrix A onto B with respect to the inner product defined on M and R. So, that is the, again you can check whether this orthogonal projection which we have obtained, that is say let me call this as a matrix M is equal to this matrix, orthogonal projection of A onto B, and then we can check that see here A minus M, this inner product with B, this should be 0. The answer is true, that is correct. So, therefore, this is orthogonal projection of A onto B. Okay, this is the matrix which is orthogonal projection of A onto B, and yeah, right. So, we can explore many more examples of inner product defined on finite dimensional vector space. So, all we need to do is define, because it may not be inbuilt already. So, you need to define it separately using DEF, or you can use lambda function for definition. Now, let me stop here. I will leave some simple exercises. So, first one is this on P3x, define this inner product and find angle between these two vectors in degree. Next problem is find orthogonal projection of this onto this with respect to this inner product. So, this example we already did, this is just different polynomials. Similarly, define this inner product and verify the cosine law under this inner product. Define the inner product this 0 to pi, now Fx Gx on C 0 to pi, and check whether the cos nx and sin mx are orthogonal to each other for any two integers m and n. And the last one is, suppose we can also define orthogonal projection onto any straight line. So, if I take a straight line y equal to m of x, mx, and then suppose we say that orthogonal projection is a map from R2 to R2, then that map let us say Pm of V can be given by this matrix multiplication. So, Pm will be a matrix, or matrix of this Pm is going to be 1 upon 1 plus m square into 1 m and m square. So, this is orthogonal projection. So, you could think of this line as a line passing through a vector. So, the orthogonal projection of a vector onto another vector, that is what is required, but you can obtain this as explicit formula. Similarly, you take, let us say, reflection about any line y equal to m of x. We have seen reflection of a vector about x axis. So, if I have a vector x y, if I reflect about x the line x axis, then it is nothing but x y will go to x comma minus y, and in this case, so if I denote this map as qm, which is a reflection about this line y equal to m of x, then this matrix of qm will be given by this and so use this definition to find reflection of a vector 2 comma 4 about the line y equal to half x, and also try to plot graph of all these points along with the line and the point which is reflection. Similarly, you should plot for the projection. Okay. So, thank you very much. In next class, we will look at some more concept on inner product.